My name is Xingyu.
My name is Yuchen Bian.
My name's Ken Church, and I'll be talking about training on lexical resources. Here's a bunch of URLs. You can stop the video here and see them all in more detail. We're going to be using this little language we call GFT. Fit takes a pre-trained model plus some data and produces a post-trained model. And predict takes an input X and applies a model, either pre-trained or post-trained, to get some estimates of labels, predictions, and hopefully the Y hats will be close to the gold standard labels Y. Here's an example of a GFT program. It takes a pre-trained model as input and some data and produces as output a post-trained model. Then at predict, you take the input X and then you get these Y hat labels. Here's the outline for what we're going to talk about today. We don't normally think of using lexical resources for training data, though you can find precedents. In this case, we're going to imagine we have an input thesaurus, which we'll use for training data, and consider the thesaurus to be a set of triples, 2 words, and a relation. And the 2 words, well, W1, W2 are words, and the relation is 0 if and only if W1, W2 are synonymous. And then we can fine tune a pre-trained model using a base model such as BERT or Ernie, and then use this relationship to fine tune. On the left, we show a small sample of the thesaurus, have a bunch of pairs of words, and you have some gold labels. And then on the right, we actually get 2 logits, a Y1 and a Y2. And if Y1 is bigger than Y2, then we believe the 2 words or the 2 input texts are synonymous. So now we can apply inference to text even though it was trained on words. So on the left, we're showing a bunch of words. Text 1, text 2 are words. But on the right, they're MUIs, multi-word expressions. Now we're going to talk about a bunch of methods and some data sets. We have 2 baseline methods. There's a mixture of experts, which is from a recent paper. It comes either with default settings or with the better settings. And then we have a proposed method, which is based on GFT. And then we have 5 data sets here. 3 of them come from that prior work. Fallows is a thesaurus that we found. And Fallows S is a sample of the thesaurus. It's a random sample. All of these splits are posted on our websites. So on the left, we see the same charts we had before, but on the right here, I want to show the 3 bold values are the best conditions where you train on one of these data sets, you test on another data set, and it's generally better if you train on the same data set as you test on. The 3 bold values here are the 3 conditions that were tested in the previous work. We're actually testing on 25 cases, all 5x5 conditions, and partly because we want to see how things generalize when the test and train are not matched. Here we're comparing the mixture of experts baseline with better settings against the proposed system on the right. On the left here, we're just showing the delta between the proposed and the mixture of experts with the better settings. And in the red values are the large deltas. So most of the deltas are pretty small. When they're small, the proposed method is close to the baseline, especially on the data sets that the baseline was designed for. The big exception is the Fallows case, where there's this huge improvement. And that's because the proposed method, I think, generalizes better to other collections. Now, more interesting, I think, is generalizing beyond the simple classification tasks that this were trained for. Let's talk about multi-word expressions, out of vocabulary, and lots of other things. So here we have on the left, the top of the left are the logits coming out of the model. The rows and columns are shorthand for these things. This is showing that the model is actually capturing undesirable biases. I think it's pretty well known that these methods are exposed to that kind of concern. Then on the bottom of the left, we're showing correlations of the top. And then the right is showing clustering of the correlations of the logits. one of the things you can see here is that there are large values in these two blocks, and those show up as these clusters. And so it's clearly somehow learning these undesirable biases. Now, out of vocabulary words. So here we took a lot of variants of the out of vocabulary word grok. What you can see is that the clustering seems to learn that there's a distinction between sort of, let me call it, the positive cases and the negative cases. So it somehow seems to be learning something about morphology and out of vocabulary words to separate the positive cases from the negative cases. How about negation? If we use the same kind of clustering approach, you see that the positive cases and the negative cases seem to cluster into two separate groups. Now, we're concerned about some kind of leakage. Many of the graphs that we were looking at are actually very sparse. You can imagine that there would be some very simple, probably too simple approximations, that synonymy is some kind of equivalence relation where there'd be some structures. So the synonymy might be symmetric and even transitive. Antonyms would have some other properties that could give rise to various leakage. And if there are clues for connecting components across splits, then we could leak information from one split to another. Now, what we see is that there actually is some evidence for this kind of leakage. So on the right, we're showing how you can go from edges in the validation set to paths in the training set. The paths of length 1 are particularly worrisome. So imagine good and awful are connected in one direction in one split and the other direction in the other split. And so if you believe that there's some kind of symmetry relationship, then you could infer from across these splits what's going on. Now, what about paths of length 2? It's probably not as bad as paths of length 1, but it's still worrisome. So here we have some examples. You can go from innocent to harmless in 2 steps instead of 1 step. And now the question is, how could we use these paths to leak labels across splits? We're going to introduce something we call A leakage. And the definition, so let E be an edge from A to B in say, the validation split. And then label sub V be the label on E in that split. And then we have a path that's defined on the training set from A to B. And we're going to then say that A sub T is the number of antonym labels on path sub T. And now the heuristic is that the label sub V, the label in the validation set, is predictable from the parity of A sub T. We use decision trees to try to test this heuristic. And in fact, the decision trees even discover this heuristic and even show how good it is. Now, here in table 11, we show that the leakage is actually quite serious, that you can get 90-some% in many of these cases, at least over applicable edges. Edges are applicable if there's a path in the training set. And from the previous previous slides, we know that there are paths in many cases. So this is really quite a concern, and results that are based on bad benchmarks perhaps should be retracted. Now, let's talk about Vad regression. So this is another resource, is the Vad set, and I point you to this URL. It's a really great resource. Vad has got a lot of history in psycholinguistics going back to the 50s. The VAD stands for valence, arousal, and dominance. There are 3 different dimensions. On the right, we're showing words that are close to open. And as you see, the synonyms have small VAD distances, and the antonyms have larger VAD distances. The VAD scores range between 0 and 1 in each of the 3 dimensions. And then on the bottom right, we're showing, we looked at correlations between these VAD distances and antonyms and synonyms, and you can see that the correlations are positive with the antonyms, that is, larger distances are more likely to be antonyms, and they're negatively correlated with synonyms because larger distances are less likely to be synonyms. The correlations aren't massive. They're not, they could be as magnitude could be close to 1. The VAD distances are kind of like the synonym-antonym task. They don't have the problem with leakage because the VAD lexicon is fully connected. That is, we have 20,000 lemmas, and for each lemma, we have a point in R3, and you can define a distance between any pair of these 20,000 words. So that's why I say it's fully connected. We changed the task from being classification to being regression. And the standard way of producing splits would be to split on edges, but we might also consider splitting on vertices. If you're interested in trying to generalize to out of vocabulary words, then maybe the splits on vertices are more relevant. Now we're kind of interested in this thing we call a morpheme diagnostic. So if you group words by affixes, say over, then you have a pair of words like overtake and take, or overlook and look, and you can measure their distances in the VAD space or in various word to vec distances. What we do is we plot words by groups based on affixes. The red lines are drawn at 0 and square root of 2. Small distances would be pairs that are similar to one another, kind of synonyms. Large distances would be like random pairs. And the observation is that VAD varies systematically. You get smaller VAD distances for affixes that you would expect wouldn't change in the synonym-antonym directions. And you get large VADs for things that are more like antonyms. So the ones on the right really are antonyms, and the ones on the left are more like synonyms. Here are the antonyms, here are the synonyms. Word to vec distances tend to be large across the board. They never really get small. Almost any pair of words is far apart. It's very hard to find. They're very rare words that are near each other in word to vec distances. Now we've got some results on the right. So we split these things. We used 16,000 of the 20,000 vocabulary words. We held the remainder out so we could test things like out of vocabulary. And generally what we found is the results are promising when the splits are large. In this case, we have 1 million words in a million edges in the training set, and they're representative of one another. In this case, they are. And we've experimented with different size training sets and different ways of splitting. And this is about the best case. We looked at a whole bunch of different base models, and you can see in all these cases that the R2 ranges, if it's close to 1, that's really good. And if it transfers well so that we train on this and we measure on that, then you see that these cases, their R2 is very large and transfers well. Unfortunately, when we look at the unseen words, that we look at the 4,000 words we held out, the transfer there is much worse. So that's a concern. We proposed a fine-tuning of deep nets on lexical resources. We looked at a thesaurus, and we also looked at Vad regression. Both of them use the same equation, but in one case, y is a categorical variable. It's either a synonym or an antonym. In the other case, y is in R3, actually it's a distance over and defined over points in R3. Proposed method is competitive with the baseline on the cases that it was designed for, and it generalizes better to a case that wasn't considered in the original paper. Then we looked at, you can train on words and make inference on text. And in this way, we could talk about MUIs, multiple word expressions, out of vocabulary words, longer texts in many languages, sentences, paragraphs, and so on. On a cautionary note, we found evidence of leakage in the standard benchmarks as well as the Fallows one. And we think there's a lot of work based on bad benchmarks that may need to be retracted. To address the concerns with leakage, we introduced the Vad regression task. Since Vad is fully connected, we could study various sampling methods. The transfer is more effective when the splits are large and representative of one another. The proposed method is effective for pairs of words in the training set, but less effective for pairs of unseen words.